Hello, my name is Jonathan Pallant and I'm a Principal Engineer at Cambridge Consultants, and this is my introduction to Rust. This was actually a talk I gave to my colleagues at Cambridge Consultants a few weeks ago. Rust is a language that I'm really excited about because I think it gives us a way of improving how we produce and deliver software. And so I was sufficiently excited about it. I wanted to share it with my colleagues and share it with you. So, what is Rust? Well, Rust is a systems programming language, and we'll come on to that in a moment. But it's one that runs blazingly fast, but at the same time prevents segfaults and other runtime errors, and guarantees your code is thread safe and free of data hazards. By systems programming language, traditionally I guess people have meant C, or perhaps C++. A long time ago I guess people might have considered Pascal a systems programming language, but they probably don't mean Java or C#, and they almost certainly don't mean interpreted languages like Python and Ruby. So by systems programming language we generally mean it's a language you can write an operating system in. It compiles down to machine code, and there's a relatively thin runtime, generally no garbage collection, and it's something you can write an operating system in. So Rust comes from Mozilla. They're using it today in their Firefox browser, in the MPEG-4 metadata parser. That's obviously a piece of code that's exposed to data that could have come from anywhere. It's critical to avoid vulnerabilities in that kind of parsing code. And so they have a code written in C++ and they rewrote the code in Rust and they pushed it out into Firefox to compare the two, and after their stat system said they'd had something like 10 billion iterations that just ran fine, they decided, yeah, this language it's good enough for production, and then are rewriting their rendering engine in it. So again, rendering engine is given all kinds of strange and weird inputs that it has to guard against. But by doing it in Rust, they can improve the performance, they can improve the parallelism, and avoid a whole bunch of buffer overflows and other runtime issues. So why should you care about Rust? Why do I care about Rust? Well, I like Rust because it's fast like C. It compiles down to machine code like C does, and it has excellent C interoperability. So you can call C routines from Rust, you can call Rust routines from C. But unlike C, as we've said, segmentation faults are impossible, null pointer dereferences are impossible, buffer overflows are impossible. Now I've qualified those with an asterisk because Rust is split into two parts, if you like. There's the safe part and the unsafe part. And unlike some other languages that have come before, like Spark, Ada, in this case, when we say a safe subset, it's the majority of the language. It's possible to be incredibly productive in safe Rust, and you shouldn't need to go to the unsafe part of the language on a normal basis. It's only if you're interacting with the hardware directly. But it gives you that option. So, unlike Java, you can drop down into this unsafe mode. You can access raw pointers. You can access your machine hardware directly, and it allows you to do those operating system parts, those drivers, and then you can go back into safe Rust. Because it's a modern language, again, unlike C, you've got a first-class build system, documentation generators, and code formatting. It all comes as part of the language. There's no discussions about which code format am I going to use. Are we using Doctrine comments? It's just this rich ecosystem that exists, and it's consistent. On top of that, there's what I've described as a rich and expressive type system. So in Rust, you're very much encouraged, I guess as you are in modern C++, to write code that expresses what you mean, as opposed to writing code that says what you think you need to say to get the C compiler to do what you want to do. But what it means is when you read the Rust code, it's much easier to understand what's going on, I think. But unlike C++, the standard library isn't massively templated. It uses generics, but the types aren't bonkers. There's a string type, whereas in C++, a standard string is actually a standard basic string typed on a allocator, typed on char, typed on char. That stuff's difficult to work with. Rust solves those problems. So if we look at the type system, you get your basic types, your integers, floats. They're all of fixed width as opposed to being arbitrary width like they are in C. You get your arrays. You get structures, so you can arrange these things together in blocks. You get your enumerations. This is all just like C. But one of the key features of Rust is what they call a tagged enumeration. So we'll come on to these in a minute, but think of it like a combination between an enumeration and a C union. When it comes to handling characters, Rust is built around Unicode, as modern languages should be. So a character is always a 32-bit Unicode scalar value. It represents any of the 16.7 million odd Unicode characters. While strings, to aid getting data in and out of your system, strings are stored internally as arrays of octets encoded as UTF-8. And at runtime it verifies that these are valid UTF-8 characters. The upside is it's easy to marshal to and from byte arrays, as you would need if you're networking and so on. The downside is it's not necessarily straightforward to find the nth character in a string, because the byte position of that character depends on the number of bytes used for each of the characters that come before it. But I think that's a fair trade-off. It's not often you need to slice strings by character. We also have this concept of a slice. So a slice is like a view into another data type. So in C, you would give someone a pointer. You say, I want to give you, the back half of my array, I'm going to give you a pointer to it, and maybe a size t, but there's no guarantee you give them the size t. Maybe you just give them the pointer and then they have to work out how long the array is or guess in some way. But with a slice, that all comes packaged as a bundle. So you can say, I'm giving you a view into my structure, and you can see this much of it. You could see the first part, the second part, all of it, however you want to do that. In C++, we also have this concept of references, and that's the same in Rust. A reference is effectively a pointer to an object, but it's one that's guaranteed to be non-null. Pointers are available, but they're only available when you go into unsafe Rust. In terms of building object-oriented code, Rust uses a trait system. So types, and even the fundamental types like scalars, implement traits. And you would normally build a struct and you would implement multiple traits. You say, this trait, this is a reader and it's a writer, and now I can use this struct anywhere I expect something that implements the read trait or the write trait. It doesn't support sort of a C++ or Java style inheritance yet. It's work in progress, but traits will cover most eventualities and avoid a lot of the problems you can have with inheritance. Related to this, Rust introduces the idea of a drop trait. So the idea is everything is RAII, resource acquisition is initialization, and so you create your objects on the stack, and then when they either get moved somewhere else or they pop off the stack when your scope ends, and at this point you can run a custom destructor by implementing what's called the drop trait. Again, as a modern language like C# and Java, Rust uses generics, but as we'll see when we talk about modules, the implementation is much cleaner than in C++. So let's look at those tagged enumerations I alluded to earlier. Here we've got an example of an enum called message, and message has 4 enumerators within it. We've got quit, change color, move, and write. But unlike in C, we can see that some of these enumerators have parameters. So change color takes 3 integers, move has an x and a y coordinate, and the write message takes a string. Now you could build this system in C by having a series of structures and unioning them together, and then you'd have a discriminator enum. But there's no guarantee that you've set your discriminator correctly for the structure you're filling in. In Rust, it's statically impossible to create a change color message and not supply the 3 integers. You couldn't create a change color message with a string. The language just doesn't allow it. And so there's a whole load of bugs you could introduce in C that you just can't do in Rust. But this leads to some very powerful concepts. So if we look at the option enumeration, this is built into the standard library and it's brought into scope in every file by default because it's so useful. In C, say you were looking at a hash table and the key might be present or it might not be present. So you either want to return some value or not return a value if it's not found. Well, in languages like C, you're forced to return a Boolean and then pass the data by reference in some pointer argument that the caller may or may not have supplied. Or you might return a pointer which could be null, but then you've got questions about who owns the data you're pointing at. Is the caller supposed to free it or not? Well, in Rust, you can express this with an option. An option is typed on some type T, and you either have some T or you have none. And again, the language makes it statically impossible for you to try and get at T without having first checked whether you've got some T or got none. If you're given none, it is impossible for your code to think that you had some T instead. So again, there's a whole class of bugs, just not possible. And expanding on that, we have the result type. So we can say, if this has worked, I'm going to give you some result T. That might be, I don't know, the number of bytes you've written into your socket. And if it doesn't work, if there's an error case, I'm going to give you some other type E. That might be a string error you can give to the user or some form of error enumeration. And again, it's these kind of concepts that allow you to write code that clearly expresses what you mean, and it's very readable code. So let's look at those trait implementations. Here I have a trait, and it's named foo, and I can say that anything that implements the foo trait has a method called method. It takes a reference to self, and it returns a string. Again, in some languages, you might think returning complex objects like strings, it's generally to be avoided in some fashion. It's expensive, but in Rust, it's absolutely the right thing to do. The compiler is clever, and it can do various eliding and move operators, so that this is not an expensive operation. This is idiomatic Rust. In the next example, you see we're implementing the foo trait for some type. In this case, I've chosen to implement it on the scalar U8, and I have a method implementation that does some string formatting. The format function ends with an exclamation mark because it means it's a macro, but in this case that doesn't matter. We can treat it like a function. And you'll notice this doesn't have a return keyword. Because Rust is an expression-based language, the result of the method function is the return of the last expression in that block. And so format returns a string, so method returns a string. Again, you can see I've now implemented foo for the string type. And then we can say let message equals some scalar U8 dot method. So we can implement traits on types, and then we can call them. You wouldn't normally call traits on a scalar integer. It's a bit too Ruby for my liking, but it demonstrates that it's possible. Okay, so let's look at memory safety in Rust. Because, as we've discussed, arrays know their own size and slices know their own size, it's impossible to run off the end of an array. It's a whole class of C bugs that just aren't possible in Rust. The Rust compiler ensures this by either inserting runtime checks. So if you're indexing into an array, there will be a runtime check to make sure that you haven't gone off the end. Or if the compiler can statically determine that it's impossible for you to go off the end of the array, those runtime checks can be removed, and that's how you get your performance. For example, if you were iterating through an array, you could say for I in 0 to array length, and that would cost you a runtime check when you indexed your array. Or you could say for element in array, and if you're iterating through the array in that fashion, Rust knows you can't go off the end. So the runtime bounds checks can be elided, and you get your performance. The next key thing about Rust is it's impossible to leak memory from the heap. That's a whole series of classic C bugs where you've done a malloc and you haven't done your free. It can't happen in Rust. Heap allocated types are wrapped in a box object. When you wrap something in a box, that means I want to store it on the heap. But that box object is like any other sort of value type, and when it goes out of scope, it automatically releases its contents. So either someone's got the box and that's fine, or the box has gone out of scope and memory is cleaned up automatically. Another classic series of C bugs is take a pointer of a stack object and then return it, and obviously function end, stack's cleaned up, object's no longer valid. The Rust compiler will catch this and it will say no, this pointer lives longer than the object you're pointing at, and so this isn't allowed, and we'll touch on that more when we look at the borrow checker. Final example of a classic C bug is dereferencing null. And as we've seen already, the option T allows you to express this idea of some or none, and we use that instead of the sense of a null pointer. And in fact, even better, the Rust compiler can work out that if type T can't be null, for example, it's a reference, then the discriminator that allows it to select between some or none is actually not required. And so an option T on a reference just compiles down to a good old-fashioned pointer as you would in C, but you've got all that compile time safety and you've got those guarantees. And of course you can break all these rules. You can just write unsafe Rust, and you can do all of these things if you want. But if you do that, at least you know if your code has these bugs, then it must be in the very small unsafe subset of your code. So hopefully you've got less code to trawl through to find those bugs. So the borrow checker. The borrow checker is a really key part of the Rust compiler. The compilation is relatively lengthy, but it's doing so much work for you. The rule is, when you have an object, you can either have exactly one mutable reference to it, or you can have multiple immutable references, so const references, to use the C terminology, but you can't have both. The example I heard is it's like a colouring book. Lots of people can look through the book at the same time. That's fine. There's no hazards there. You can all look. But if someone wants to do some colouring in, they've got to sort of pick up the book, take it away from everyone else, do the colouring in by themselves, and then once they're finished, they can bring it back. And that way you avoid all of these thread safety issues, these race hazards. Now, the Rust compiler checks all this at compile time. It's tracking the lifetime of all the references and all of the objects, and it can check that, no, I've got two references at the same time, and one of them is mutable, so you need to clean this up. And as with many things in Rust, you can bypass this. You can sort of turn this off. You can create immutable objects that have mutable data inside them, but you have to call special access methods to get at that, and that then inserts runtime checks. An example is a mutex object. A mutex object is immutable. We can pass that round. But if you want to access the data inside, you need to call the lock method, and then you get your runtime checks. So let's look at one of the key parts of Rust in terms of syntax, and that's pattern matching. And we'll look at that as part of the match statement, which I like to think of as a switch statement on steroids. So I've declared some function called getValue that returns an optional integer. It's either sum i32 or none. And our test function says let x equals match getValue. So we're going to call the getValue function and we're going to match on the result. And if I get sum I, where I is more than 5, I return a string. If I get sum anything else, it's a different string. And if getValue returns none, then I'm calling the report fail method and I return some other string. We see we didn't have to specify the type of x because the compiler was able to work it out. The type of x is a reference to a string literal. So that helps you, reduces the verboseness of your code, makes it easy to read. And then we have a println call. It's like println in C, so we'll print the value out. So we can do lots of clever things in the match statement here. And it's a really powerful way of forcing you to handle your results. If you're calling getValue, then you can't get at that integer unless you've unwrapped it, either in a match statement or using something equivalent like a let expression. So another one of the key parts of Rust that makes it so usable on a day-to-day basis is the module system. If you're a C or a C++ programmer like me, its header files are so arcane. They feel like they're from the past. They're complicated. It's difficult to arrange them neatly. The text substitution just doesn't really fit with a modern language. But in Rust, we don't have header files. It's like Java. We can declare types. So we declare a struct foo, and that's hidden by default. It's only available in the module. And we can say, I've got some pub structure, bar, and now bar is public, and other people can import bar from my module. I would use a use statement. I can say, use my module, in this case, two things, baz and quux. Another really neat feature is you can import items from another module and then re-export them as if they were your own. This can be really useful, for example, if I had a GPIO library for an embedded system and I supported multiple processors. I could use conditional compilation to say, well, if I'm on Texas Instruments T/C, then pub use T/C, GPIO write. Whereas if I'm on some ST platform, I could say pub use STM32 GPIO write. And all people would need to know is they're using the GPIO write function in my module, but I'm at compile time rerouting that to another definition somewhere else. Key difference when it comes to macros is that in Rust the macros are operate on an abstract syntax tree. It's not text substitution, it's much more advanced than that. You can do much cleverer things. So another one of the things I do on a regular basis in C is I've got some data structure and I want to render that data structure to the console or to some debug output. And so in Rust, we can say this is implementing the debug trait. So I'm using the standard format library, I've got my point structure with an X and a Y, and I'm implementing debug for point. And I've got a routine that renders out a nice string. It's a nice representation of my point. And now whenever I've got a point, I can call println or format, and if I use the : operator, it renders it using this debug trait, and then I get my nice textual representation. And the nice thing here is that the rendering function lives with the definition of the type. If you were doing this in C, you might have to rewrite that rendering code, that sprintf string literal, all over the place, wherever you were outputting your text, whereas here, it can be written once next to the definition of the type. It's easy to keep them in sync. And of course, Rust's even better than that, because if I just say derive debug, for almost all common structs and scalars and arrays, it can generate this for me. So it generates an automatic formatting function. So moving on to look at the standard API, Rust in many ways reminds me of Python, in it has this rich standard API that's full of useful types. So things that you might have to go and write from scratch in C, like a B tree or a binary heap, they're all included, they're all performant, they're well tested. You've got access to socket code, networking code. It's easy to spin up threads, processes, pass messages between processes and threads using queues and channels. You've got code for file system on I/O, and it's all there, and it's really easy to use. And it's because it's a modern language. C predates the idea of a large standard library, or even being able to download modules from the internet. Whereas with Rust, it's all available in the standard API, and there's a standard mechanism for going and getting more. Now that mechanism is cargo. So cargo is the build system for Rust. Rust is full of puns, you'll quickly come to realise. So the code you write in Rust, the collection of modules, is known as a crate, and then cargo is the system for moving crates around and building crates. So it's a really nice, easy build system to use. So we can create a new cargo project. If I want to build it, I type cargo build, and it builds all my code. And if I say cargo run, it builds it if required, and then executes it. It just couldn't be simpler. Rust has got a built-in unit test system, so I can qualify my modules and functions with a test directive, and then that means if I run cargo test, all of my tests run, and it gives me a report, around 15 tests, 14 passed, this one panicked, here's your back trace. You can do this sort of thing in C, but it's not built in. People have different ways of doing it. It's so nice when it's all built into the language. And as a neat extension, there's a benchmark function. I can qualify some of my functions with a benchmark directive. If I was writing an AES engine or some kind of compression routine, and then if I type cargo bench, or if anyone else runs cargo bench on my crate, then it will repeatedly run that routine until it's got reliable results and it can report performance. So for a crypto library, you can imagine how that's really useful. You can also pull down modules from the online package repository and install them on your system. Just type cargo install, it downloads, builds, you're ready to go. So how do we describe our crates that we write? Well, the definition is in a format known as TOML, and it's a lot like a Windows INI file, really. So we have our package section, name, version, and authors. You can specify license, all the normal things in there. It's worth noting the versioning is strictly semantic versioning. So we have our major, minor, and patch, where if the major is naught, that means you can break things between each minor revision. So I've got Hello World, it's a version 0.1.0, and I depend on two other libraries. I'm using the time library, or the time crate, and the regex crate. And Cargo will track these, and it will up issue them if required, and it'll make sure I'm always using compatible versions. So where does it get those packages from? Where it gets the crates from? Well, it gets them from crates.io. This is the Rust package repository. Have a look on there. There are loads of packages available, loads of crates available. They're named on a first come first served basis. So sometimes the best crate for what you want to do doesn't necessarily have the most obvious name because somebody took the name first. But have a look around on there, and there's loads of great stuff. We've got HTTP frameworks, we've got asynchronous I/O frameworks. There's loads going on. It's really interesting. Another key part of Rust, as I mentioned earlier, is the documentation generator. It's as simple as type cargo doc. It runs through your code, it pulls out the comments, it produces this beautiful HTML. It's so good. Rust, obviously, they believe in dog fooding, or drinking their own champagne, as a colleague once urged me to refer to it. So the standard library documentation is all built with cargo doc. It's all written in Rust. They type cargo doc. It's uploaded to the website. And there are various tools you can get to upload it to your own github.io or pages like that. And again, at the beginning, I mentioned a code formatter. Well, in this case, we have to type cargo install Rust format because it's not yet bundled as standard. But once you've done that, you type cargo format. The code is rendered beautifully. There's no more arguments about formatting, no more arguments about what do I need to supply to A style to meet my company standard. Let's all just agree we're going to run cargo format before every commit. Nice and straightforward. So I've said, there's loads of great things about Rust. Surely there's a catch. Nothing can be this perfect. Well, there is some bad news, I'll be honest. One of those is that if you're compiling for bare metal platforms, you are into an unstable feature set. Rust runs a release train with stable, beta, and nightly releases, and you can only access the unstable features in the nightly builds. And unfortunately, if you want to compile for bare metal, you need those unstable features. They're working on it heavily. It's not going to be too long before that problem's resolved. Another minor issue is the binary format's not yet stable. So if you're passing compiled libraries between users, you've got to make sure you're using the same version of the compiler, because say Rust 1.9 and Rust 1.10 don't agree on the binary format until it's been stabilized. But seeing as most Rust code is shipped to source, that's not a problem at all. And one complaint you often hear is that the compiler's not fast. No, it's not, but they're working actively in this area. Improvements with incremental compilation and the new medium level internal representation. It's going to make things much better in that department. But it's not too bad. It's just a bit slow. So that's it. Hopefully I've whetted your appetite. I've got you excited about Rust. You want to go and learn more? Well, to do that, you can go to the website rust-lang.org. You can look at the great book, which has been written by Stephen Carroll. It's a great reference. There's so much detail in there. You can go to the API documentation, which is generated from their API source code. You can drop on the Reddit. You can look at the user forums. There are great weekly roundups like This Week in Rust. There are great podcasts like New Rustation. Or we've got guys at Cambridge Consultants who are really interested in this sort of thing. So get in touch. That's it. Thank you very much.